Hey everyone, welcome to another video of Learn to Code. I'm here with the mechanical engineer. How you doing?
Fantastic. How about you?
Good. So last time we did a brief introduction to recursion. We kind of did the classic example of computing the factorial of a number, right?
hmm
So do you remember what the really basic general idea of recursion is?
Yeah, it's just you can kind of keep calling a function inside of a function, and
Right. So
you just kind of loop through it as many times as you want.
yeah, so it's when a function calls itself, basically. So it's a
hmm
really great way to kind of take a big problem and split it up into smaller problems. If you know that you're going to be doing really similar things every time, meaning you call the same function every time.
hmm
So are you familiar with the Fibonacci sequence?
Yeah.
So what is that?
I think it starts at 0 and then 1 and then 1, 2, 3, 5, 8, 13, and onwards.
Right, so it's basically the nth Fibonacci number is the sum of the n minus 1 plus the n minus 2 Fibonacci number.
hmm
So what we're going to do today is we're going to do focus on kind of the trade-off between a recursive approach and an iterative approach. So
hmm
iterative is just basically when you do things with loops, like while loops or for loops, right? Usually while loops if you're kind of combining them. But
hmm
um, so we're going to look at when it makes sense to use recursion and when it might make sense to kind of flatten that out into a iterative approach. So why don't we start off by just declaring a function called fib, and this will take in a number n. Great. So now, knowing that the Fibonacci sequence is just adding up the Fibonacci sequence of one before and two before, what would
hmm
you put here for a recursive call to achieve that?
Um, I would do something along the lines of um, so we need to call fib again, our our function here, but we want to do n minus 1 and n plus 2, correct? So I think this is kind of a necessary component.
Yeah, so that's going to be the kind of like where the recursive calls start. So you can actually return that line there, just so we can have a return statement in our function. Um, Now, the problem is though, is if I gave you, this doesn't really do anything, right? Because the function itself doesn't, it'll only return these calls that return other calls and so on forever, and it really doesn't do anything, right?
Yeah.
So if you remember from last time, we had the concept of base cases.
hmm
So what base cases can you think of for the Fibonacci sequence?
Um, if it's 0, we don't want to go farther than like -1. So once we hit 0, we kind of want to stop.
Yeah, like a stop, right?
hmm
Right. So why don't you add in that base case above your return there so we make sure it gets executed before all the functions.
So if n equals 0, um, we want to return 0.
Yep, because that's what the zeroth Fibonacci number is, right?
Yeah.
Then because you had two recursive calls, so n minus one and n minus two, what's going to be sort of the what we're accumulating? Like what's going to what's when do we want to stop, but then also begin to build our sum for the Fibonacci number?
I think that happens at n equals 1.
Yep. And then what's the first Fibonacci or the Fibonacci number one?
Um, is 1, I think, right?
Yeah.
Okay. So n equals 1, right?
Yep.
One.
Turn one, right? And then just on line two there, you have a triple equals. I don't know if you were doing some JavaScript earlier, but
Sorry.
no, you're good. All right, so why don't we just call this function with, say, 5, and we'll see what we get. I believe the fifth Fibonacci number is 5, so I would hope that it returns 5. I could be wrong, though. But why don't you just go ahead and run this. There you go.
Okay.
So now this is great, right? So basically what's happening is every time you run this, yeah, and if you want to just put it up there at the top, that'd be nice. So every time that you run this, it's basically nothing happens until n equals 0 or n equals 1 in terms of accumulating a sum, right? So if you start to think about it, when n gets really, really large here, because kind of look at the way that it grows, like The fifth Fibonacci is 5, but then 8 is now 21. So this
Mhm.
sum is increasing really quickly, right?
Yeah.
So because we just said that the only way that this is sort of incrementing any sort of count to actually give us our answer, that means that the number 1 is going to be added that many times. So if you put the call to fib of 8, that means that 21 ones are going to be added together.
Mhm.
So as n gets really large, this could become really inefficient.
Yeah.
We can start to think of maybe a better way to do this, and that's going to be the iterative approach. So to start with that one, why don't you just make a new function called like fib I or fib iterative, and then that'll also take in n. Right. So now in here, I'm going to introduce you to this thing called multi-assignment.
Mm-hmm.
Single line multi-assignment. So why don't we make two variables here called old and new, so old comma new, and you can set that equal to 0, 1. So this is something cool that Python has. So basically what we're assigning here is a variable called old that is 0 and a variable called new that is 1.
Mm-hmm.
So you can think of new in this case as kind of what we're accumulating, like as we go, right?
Mm-hmm.
So to do that, we need to loop up until n because we want the nth Fibonacci number. So you can do for I in range. And we can probably do n minus 1 here. I'll show you. And then all you have to do here is just think of how to reassign old and new so that new is always old plus new. So to do that, you can think of us as stepping through that list you have at the top there. So you can say old comma new. And then that's going to be equal to new comma old plus new. So what we're doing here is we're reassigning new to whatever the old was. In the first iteration, it's 0, plus new in the first iteration, it's 1. And then basically then assigning old to be our new element to kind of move 1 to the right. That makes sense?
Yeah.
All right, cool. So now there is one weird case here. So what you're going to want to return at the end here is just new. New is going to be our Fibonacci number. So now if I give you fib of 0 here, what do you expect it to return? And then what does our function return here?
We expect it to return 0.
Right.
But it's going to be for I in range up until -1. So I think that would be kind of an issue.
Yeah, so what we can actually do is just catch this right on line 16 there, and you can just say when n is 0, we just want to return 0.
If n equals 0, return 0.
Yep. So that kind of catches that weird case, and now we have our nice multi-assignment there, and it looks, it's only a few lines of code, and it looks pretty nice. So why don't you run this one? We'll test it with 5 and make sure we get 5. There you go. So now I kind of touched on this at the beginning, but we can start to talk a little bit about the runtime of these algorithms. So we talked about how in the first one, we're going to decompose this all the way down into ones no matter what, right? So as n increases, our calls to fib are going to increase exponentially, really, right? It'll basically go by a power of 2 for every single one over and over again. So that can become really costly. And as n gets huge, if you were to time this, you'd see that even with n equal to 30 or 40, it takes the first one about a minute to run. Where in the second one here, we know that the only sort of computation that we're doing is on line 20 there and 21. So 20 is going to run n times, basically, right? Or just n times. And so in that last example I just talked about, when you have n equal 30, we know that this loop is only going to run 30 times. So, or really 29 times. And it's just doing this reassignment, where in the top one, we would have 30, and then that would break down into 29 and 28, and then that would have 4 calls, 8 calls, 16, 32, and so on, right?
Yeah.
And I think that Fibonacci number has got to be in the millions or maybe even the billions. So if you think about adding 1 that many times, even you can even just think of yourself adding this up on a calculator. It's a lot easier to just add numbers as they get bigger, like we do on line 21, than it is to add 60 million billion times, right?
Mm-hmm. Yeah.
So that's just something to keep in mind when you're sort of approaching a problem. Another downside of using recursion like this is sometimes something like Fibonacci is sort of, it's easy to understand. Everybody in this field or in some STEM field will know what that is. But sometimes if you have like a custom functionality and you're using recursion, it can be kind of hard to follow, especially if there's nested things going on and everything. So in general, I would say with n really small here, I think the recursive will run faster than the iterative in this case. But I would say for a more general solution, the iterative is probably the best move. And you get to do that cool thing on line 21 multi assignment. You don't have to worry about temps or anything. That's what that Python has. So yeah, so that's sort of the trade-off between recursion and iterative solutions. So you have any questions on this one?
No, I think I'm all set.
All right, awesome. Well, good job.
Thank you very much.